For LM3, we are going to be focusing on using the big three equations for kinematics again. I'm going to go through all of them with the exception of question number 3 because we did that one in class. So the first one says a firework shell is accelerated from rest. So that is going to be our initial velocity, v0. The final velocity is 50 meters per second, and the distance, delta x, is 0.23 meters. It's actually easier to solve part B first before solving part A, so I'm going to go ahead and do that. I have v, v0, and delta x, so v, v0, and delta x right here, and solve for A. So v squared is v0 squared plus 2a delta x. V squared is 50 squared. That equals 0 squared plus 2a times 0.230. 50 squared is 2500. That will equal 0.46a. Solving for a. You'll get an acceleration of 5,435 meters per second squared. And then solving for part A, now that we have an acceleration, we can use the first equation. We couldn't originally because we had two unknown variables. This will be 50 equals 0 plus 5435t. Divide out the 5,435. And you'll get a time of 9.20 e negative 3 seconds, or 9.2 milliseconds. To confirm those answers, moving on to 2. Swan on a lake needs to reach a speed of 4.9. It starts from rest, and we have the given acceleration of 0.315. So once again, we'll start with the third equation. V squared is v0 squared plus 2a delta x. That'll be a 5.9 squared equals 0 squared plus 2a times 0.315. I apologize, we're actually given the acceleration. So that'll be a 2 times 0.315 times delta x. You get 34.8 equals 0.63 delta x. Delta x will be 55.2 meters. To solve the time, we'll use the first equation. 5.9 is 0 plus 0.315 t. 5.9 divided by 0.315 gives us a time of 18.7 seconds. So this is an incredibly slow swan. (55.2) and 18.7. Once again, number 3 was done in class, so I'm going to skip it and move on to 4. In 4, you have a person in the water calling out for help, and the helicopter above them is going to drop a life preserver. So here's our life preserver, and it's being thrown downwards with an initial speed of 2.08 meters per second. And we see that we are given a time of 2.4 seconds as well. The third thing that you know, although it's not explicitly told to you, is the acceleration will be negative 10. And the reason why we know that is because of gravity. So if I want to find how high the helicopter is, I'm going to go delta y is v naught t plus 1/2 at squared. The number one mistake that people make in this is they do not make the 2.08 negative. It's negative because they are throwing the life preserver downwards. And the second thing is on the 1/2 at squared, people tend to forget to put in the square. Solving out delta y will give us a negative 33.8. The question is asking how high up is the helicopter, so I'm going to use a positive 33.8. Takes us to 5, the dolphin. In 5, here's the water. You have a dolphin leap out of the water with a speed of 13.8 meters per second. And it reaches some peak up here. As discussed in the previous class, the velocity of an object at its peak of the trajectory will be 0. And the other thing that we know is, once again, the acceleration will be negative 10. So we know y initial. Y initial is 0. The dolphin starts at the water. V initial is 13.8. And the acceleration is negative 10. So we can use v squared is v initial squared plus 2a delta y. 0 squared will be 13.8 squared plus 2 times negative 10 delta y. 13.8 squared is 190. Divide out the negative 20, and you'll get 9.5 meters. The solve for the time, we'll go back to the first equation. V is v naught plus at. So 0 is 13.8 plus negative 10t. Move the 13.8 to the left side. Divide out your negative 10. You get a time of 1.38 seconds. Now the catch is you're going to have to double that time. What you've recorded so far is the time it took from the dolphin to leave the water and reach the peak. But then the dolphin's going to have to fall back down. Fortunately, due to symmetry, if it took the dolphin 1.38 seconds to go up, that means it took the dolphin 1.38 seconds to go down. And therefore the total time the dolphin is in the air is 2.76 seconds. So 9.5 and 2.76. As a reminder, you did not have to submit a file. Last one with the kangaroo. This is actually the same thing as the dolphin question, with one minor detail that's different. Instead of being told the initial velocity, you're told the height. But the kangaroo at the peak velocity will still be 0, acceleration will still be negative 10. And we're still using v squared as v naught squared plus 2a delta y. So 0 squared is v naught squared plus 2 by negative 10 by 2.12. And that will give us 0 is v naught squared minus 42.4. Move the 42.4 over, take a square root. The initial velocity is 6.51. And we can finish with the first equation. V is V naught plus AT. Just like in the dolphin, we will have to double the time. So we solve a time of 0.651 seconds. 0.651 times 2 is 1.30. 6.51 and 1.30. And there we go.